Taylor polynomials and approximations. The goal of this section is to use polynomials to approximate more complicated functions, since polynomials are easier to work with. We do this by choosing a point at which to center the polynomial, and this point guarantees to be exactly the same on both the original function and the polynomial function. So consider the function y equals e to the x. Create a polynomial to approximate y equals e to the x at the point 0, 1. So the polynomial is going to be the equation of the tangent line at that point. So if y equals e to the x, the derivative is also e to the x. And if x is equal to 0, then y prime is equal to 1. So now the equation is y minus y1 is equal to m times x minus x1. So y is equal to x plus 1. So this is my first degree polynomial. So I'll call it p1 of x is equal to x plus 1 or 1 plus x. To improve the approximation, I'm going to use the second derivative, which means I have to add another term to the original polynomial. So if y is equal to e to the x, y prime is also e to the x, and y double prime is e to the x. So my second degree polynomial is going to be 1 plus x plus some coefficient of x squared. The second derivative of the original function at 0 is equal to 1. So p2 prime is equal to 1 plus 2 times that coefficient times x. And then p2 double prime is equal to 2 times that coefficient. I want this value to agree with the second degree of the polynomial, or the second derivative of the polynomial, which implies 1 is equal to 2 times that coefficient. So that coefficient has to equal 1/2. So now my second degree polynomial is 1 plus x plus 1/2 x squared. If I continue the pattern, I'm going to add another term and call it a third degree polynomial. So 1 plus x plus 1/2 x squared plus some coefficient of x cubed. So three derivatives. If y is equal to e to the x, y prime is also e to the x, y double prime is e to the x, and y triple prime is e to the x. So the first derivative is equal to 1 plus x plus 3 times the coefficient x squared. The second derivative is 1 plus 3 times 2 times the coefficient of x. And then the third derivative, p3 triple prime, is 3 times 2 times that coefficient. The third derivative of the original function at 0 is equal to 1. So I want 1 to equal 3 times 2 times that coefficient. So that coefficient is equal to 1/6. So now the third degree polynomial, p3 of x, can be written as 1 plus x plus 1/2 x squared plus 1/6 x cubed. And if you graph this function, as I move further and further away from the point of tangency for the polynomial of degree 1, you're going to see that the function lies directly on top of y equals e to the x. And you can keep expanding this out. I just stopped at a third degree polynomial. Before the definition, if I continued this pattern, an nth degree polynomial for y equals e to the x is going to be 1 plus x divided by 1 factorial plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on, plus x to the n divided by n factorial. And this can be written as a series. Definition. If the function f has n derivatives at c, then the following is called an nth Taylor polynomial for f centered at c. So polynomial of degree n is equal to f of c plus f prime of c divided by 1 factorial x minus c plus f double prime at c divided by 2 factorial times x minus c squared plus f triple prime at c divided by 3 factorial x minus c cubed, and so on. The nth term is the nth derivative at c divided by n factorial times x minus c to the n. As a series, this can be written as the sum as I goes from 0 to n of f I at c divided by I factorial x minus c to the ith power. If the center is 0, so if c equals 0, the polynomial turns into f of 0 plus f prime of 0 divided by 1 factorial times x minus 0, or just x, plus f double prime at 0 divided by 2 factorial times x minus 0 squared. And this pattern continues, plus f n at 0 divided by n factorial x to the n. Is called the nth Maclaurin polynomial. Find the nth Maclaurin polynomial for f of x equals e to the negative x, where n is 5, so degree 5. Okay, if I start with the function, so f of x is e to the negative x. F prime of x is negative e to the negative x. F double prime of x is e to the negative x. F triple prime of x is negative e to the negative x. The fourth derivative is e to the negative x. And then the fifth derivative is negative e to the negative x. When x is equal to 0, f of 0 is 1, f prime of 0 is negative 1, f double prime of 0 is 1, and I'm plugging in 0 since it's a Taylor polynomial, which means the center is at 0. F triple prime at 0 is negative 1. The fourth derivative at 0 is positive 1. Then the fifth derivative at 0 is negative 1. So the fifth degree polynomial is 1 minus 1 over 1 factorial x plus 1 over 2 factorial x squared minus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth minus 1 over 5 factorial x to the fifth, which is equal to 1 minus x plus 1/2 x squared minus 1/6 x cubed plus 1 over 24 x to the 4 minus 1 over 120 x to the fifth. The infinite polynomial, so p sub infinity of x, or the series for this function, can be written as the sum as k goes from 0 to infinity of negative 1 to the k divided by k factorial x to the k power. Find a third degree Taylor polynomial for f of x equals sine x at x is equal to pi. So first the function is sine x. The first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. At pi, f of pi is 0. F prime of pi is negative 1. F double prime of pi is 0. F triple prime of pi is 1. So the third degree Taylor polynomial is equal to f of c plus f prime c divided by 1 factorial x minus c plus f double prime at c divided by 2 factorial x minus c squared, and so on. F of c is 0 minus 1 over 1 factorial x minus pi. F double prime is 0. So plus 0 over 2 factorial x minus pi squared. And then plus 1 over 3 factorial x minus pi cubed, which is equal to negative quantity x minus pi plus 1/6 x minus pi cubed. At x equals pi, they're the exact same. So if I plug in sine of 3 into the calculator, I get 0.14112. This third degree polynomial at pi is approximately equal to, oh, not at pi, at 3. And I picked 3 because 3 is close to pi. 0.141119. So with only 2 terms, or with only a third degree Taylor polynomial, the calculator value matches very closely to the function that I came up with, or the polynomial function that I came up with. Find a Maclaurin series for y equals sine of x. So the function is sine of x. The first derivative is cosine x. The second derivative is negative sine x. The third derivative is negative cosine x. The fourth derivative is sine x. And the fifth derivative is back to cosine x. At x equals 0, that's 0, that's 1, that's 0, that's negative 1, that's 0, that's 1. So the function can be written as 0 plus 1 over 1 factorial x plus 0 over 2 factorial x squared minus 1 over 3 factorial x cubed plus 0 over 4 factorial x to the 4th plus 1 over 5 factorial x minus 0 to the 5th, or just x to the 5th, which is equal to x minus x cubed over 3 factorial plus x to the 5th divided by 5 factorial minus x to the 7th divided by 7 factorial. And that pattern continues. So the series can be written as the sum from 0 to infinity, negative 1 to the n, x to the 2n plus 1 divided by 2n plus 1 quantity factorial. So Maclaurin series is also an infinite series. Find a Taylor polynomial fourth degree for f of x equals natural log x centered at c is equal to 1. So the function is natural log of x. The first derivative is 1 over x, which can be written as x to the negative 1. The second derivative is negative x to the negative 2 power. The third derivative is 2x to the negative 3. The fourth derivative is negative 6, x to the negative 4. At 1, when x is 1, f of 1 is 0, f prime of 1 is 1, f double prime of 1 is negative 1, f triple prime of 1 is 2. The fourth derivative at 1 is negative 6. So the polynomial of fourth degree is equal to f of 1 plus f prime of 1 divided by 1 factorial x minus 1 plus f double prime at 1 divided by 2 factorial x minus 1 squared, and so on. So the fourth degree polynomial is equal to f of 1 is 0 plus 1 over 1 factorial x minus 1 minus 1 over 2 factorial x minus 1 squared plus 2 over 3 factorial x minus 1 cubed minus 6 over 4 factorial x minus 1 to the 4th. So if I simplify this, x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed minus 1 over 4 x minus 1 to the 4th. The accuracy of these approximations are determined by the function is equal to the polynomial of degree x plus Rnx, or the error in approximation. So the error is equal to the absolute value of Rnx, which is equal to f n plus 1 z divided by n plus 1 factorial times x minus c to the n plus 1. And z is chosen to maximize the nth derivative. So if e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. X to the n over n factorial. So e to the 1 can be written as approximately 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on, plus 1 over 5 factorial. Whatever's left over is Rn of x. So I'm going to choose z to maximize f n plus 1 z on the interval 0 to 1. So if f of x is e to the x, the n plus first derivative, fn plus 1, is also equal to e to the x. The maximum of that function on the interval 0 to 1 is e. So when c is equal to 0, x minus 0 to the 6 is equal to 1 minus 0 to the 6, which is equal to 1. So the next term is 1 over 6 factorial, which is 1 over 720. So R6 of x is less than or equal to e to the first divided by 6 factorial times 1 minus 0 to the 6th. That's the next term, with the maximum on the interval 0 to 1 being e, which is equal to e divided by 720. So the error in using 6 terms to approximate e is less than e over 720.